Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Gwen Hanley with us today. Hello, Gwen.
Hey, Frank. How's it going?
I'm doing awesome on this September 16th of 2024 as we record this. And that's a very awesome background picture you have behind you there, Gwen.
Oh, thank you. We're on I/O today.
And we'll be covering I/O today, so very good. And Gwen, what's your geolocation? Where are you at?
I'm in Oakland, California.
Oakland, all right, Bay Area. Woo. Let's see, in September, so that part of California is probably coming into some of its best weather, as I think, as it's coming
Oh,
up
yeah.
in
It's been
October.
gorgeous. It's a
Yeah,
little cloudy today, but maybe it'll clear up this afternoon.
okay. And I'm in Phoenix, and we are getting a little bit of cloud today, and we're definitely cooling down. We're like in the 70s or something in the
That's
morning.
a release.
So yeah, very good. And Gwen, what is your position there? Where you're at?
Yeah, so I'm at the Berkeley Space Science Laboratory. I just got my PhD in May 2023, and now I'm an assistant research scientist.
All right. Well,
Yeah,
congratulations, Dr. Hanley.
thank you.
Awesome.
It'll sink in one day.
Yeah, very good. And as long as we're talking about your PhD and your current work situation, what is it you like to do for research?
Yeah, so I'm mostly a space plasma physicist or planetary scientist. So that's just fancy words. That means I do plasma physics near
Yeah.
planets. So I mostly work on Mars. I've been on the Mars Atmosphere and Volatile Evolution or MAVEN mission since I was an undergrad.
Cool. Very
And
cool.
now I'm actually now the deputy instrument lead for one of our science instruments. So it's been a long, exciting journey.
Journey, I was gonna say,
Yeah.
that's quite a ride.
So for me, IO is very much not in my wheelhouse. When you think IO, you think volcanoes and geology, and that is very much not my expertise. And so it was really fun to get to do the project we're going to talk about today, uh,
Cool.
which was something very different for me.
Nice. And let's go ahead and go to this very lovely PSJ article, Planetary Science Journal. It is open access. It's the open access era, people. You can go grab a copy for free. The Vulcan mission to EO. Lessons learned from the 2022 JPL Planetary Science Summer School. And Gwen, take us away.
Yeah, great, thanks. So the JPL Planetary Science Summer School, I'll just explain before we get into it. It's sort of a training exercise for graduate students and recently graduated folks, both engineers and scientists. And there are 2 sessions every summer.
Okay.
And a team of 18 students and postdocs and early career engineers all come together and design a planetary science mission from the ground up. So you
Nice.
start from the announcement of opportunity, which tells you, what kind of missions you're allowed to propose. For example, are you going to go do comet sample return or asteroid sample return or IO observer or something like that? Sorry if you can hear my cat.
Oh, good. Love them.
And the announcement of opportunity or the AO also tells you things like budget and how long the mission can be and things like that.
Right.
Starting from there, you as a group pick what kind of mission you're going to do, and then you design the whole thing. And by the end of the summer, you have a completely mature mission design with science goals and a spacecraft design and the orbit and everything all worked out. So it's a really cool experience, and it's sort of the kind of training that you don't get to do most of the time because most of the time you're doing this for real, right? So
Yeah.
exciting to have this in sort of a simulated environment where they try to make it as realistic as possible and really prepare you for doing these kinds of things later in your career.
Very cool. So are all the co-authors here participants in the school?
Yeah, so everyone except the last 3 co-authors are the students, and then the 3 at the end are the mentors. So Troy Hudson, Jennifer Scully, and Leslie Lowe's really could not have done any of this without them. So shout out to them.
Good. Very good. Okay, let's go ahead and get into it here. your intro.
So for my session, we designed a mission to Io and we called it Vulcan, who is the volcano god.
Mm-hmm.
There have been a couple of other missions to Io or designed and proposed, but not ever launched.
Right.
So one that was done in the Planetary Science Summer School was called Fire, or Flyby of Io with Repeat Encounters. And then one that was proposed for real to a Discovery class call for NASA is called the Io Volcano Observer.
Mm-hmm.
Unfortunately, it was not selected, although it was advanced to the concept study phase. So hopefully they will propose again and maybe
Oh yeah.
the second time. So we tried to avoid info about them as much as possible, but we ended up with a really similar mission design to IVO in the end. So that was really exciting for us because it told us that we sort of did a good job.
Yeah, good.
And you can see in the figure one, our logo and then our mission patch, which were both designed by different members of our team.
Very nice.
So we're really lucky to have some really great artists on the team.
Mm-hmm.
And they just did a fantastic job capturing, the spirit of
Cool.
the mission. So
Very nice. And in general, are these undergraduates, high school students? Where they?
no, so it's mostly graduate
Grad
students
students.
and postdocs. Yeah.
Okay, good.
Yeah. So
Nice.
there's been a lot of previous study of Io, both from the ground and from missions like Galileo and Juno that have gone to Jupiter. But there's never been a dedicated Io mission. And Io is really exciting because it's the only body in our solar system that could potentially have a global magma ocean hiding under the surface. And if that doesn't excite you, then I don't even know what else to say because it's just so exciting to think about, an entire planet covered, or moon, I guess, just covered by a global magma ocean. It's not clear if that can really happen, but the only way to know is by going to Io and checking, right?
I did read the other day that I forget where I saw it, but I saw something that there was a new volcano.
Yeah.
Yeah.
Yeah, I just saw that
But-
too. So
yeah.
Juno has been flying by well, it's in the Jovian system, right? And it flew by
Mhm.
Io last year and then again this year. And I think on this year's flyby, they took a picture of a region on Io that had been imaged in the past by Galileo. And in the new Juno image, there's a huge new volcano that was not there when Galileo was there back, I think, in the 1970s.
Something like
And Io is the most volcanically active body in the solar system because it's got the gravity of Jupiter, which is, huge. Io is the
that.
closest of the Galilean moons to Jupiter. And it just has incredible tidal forcing as
Yes.
it goes around Jupiter in its orbit. And so it's constantly being stretched and compressed by this huge giant planet's gravity well. And so you can imagine that it's a very violent place. I would not want to visit personally, but I definitely think we should send a spacecraft.
Absolutely. Absolutely. Very cool.
Yeah, so let's see. In terms of open questions at IO, this part of the paper is not intended to be um, a comprehensive introduction to every question about IO because we would be here all day if we talked about that.
Right.
But we tried to just sort of set the stage for the science questions that the Vulcan mission was going to address.
Okay.
And so the first part is about the structure of Io's mantle. So like I was just saying, is there really a global subsurface magma ocean?
Mhm.
But a different way of saying that is how differentiated is the mantle of Io?
Ah,
And so what that means is differentiation is this process by which the elements inside of a planet or a moon separate by mass, and the heavy metallic stuff sinks into the core, and then the lighter stuff can stay sort of dispersed throughout the mantle.
okay.
Um, and Io, because it's so volcanically active, it's constantly spewing out the inside onto the
Yeah.
surface,
Yeah.
right? So by measuring the composition of the lavas that are covering Io's surface, you actually get a window into its interior in a way that you can't really do at any other solar system body. So it's really
Very nice.
a great opportunity to look at the inside of the planet by looking at the outside.
Very good.
So in table one, we've summarized the key measurements that would be needed to address each of the open questions that Vulcan is going to look at or would look at if it were a real mission, which unfortunately it's not.
Soon.
Yeah, well, hopefully. Unfortunately, everything developed through PSSS is just for educational purposes only, and you don't get to propose it for real. But hopefully the Io Volcano Observer can go and answer all these questions for us.
Mm-hmm.
So
Okay.
in order to look at the presence of a magma ocean, we can look at things like magnetic field measurements. We can measure things like the tidal love numbers, which tell you about how the surface of a body gets deformed under different gravitational conditions, so different tidal forcing.
Uh-huh.
And then something called the libration amplitude, which tells you about how much a body is wiggling around its rotation axis. And we'll have a figure to look at that in a minute.
Uh-huh.
And then, like I said, for the differentiation state of the mantle, we can look at the composition of the lavas on the surface.
Mm-hmm. Yes, definitely.
So there's a couple other open questions that we want to look at. So no one really understands how heat is dissipated from Io's core to its surface. If you measure all of the heat coming out of the volcanoes on the surface,
Oh, yeah. Mm-hmm.
then compare that to the amount of heat measured, if you just take like full disk images,
Yeah.
something like half the heat is unaccounted for by the volcanoes. So there's this question of how is this heat being dispersed? It's got to come from somewhere. And it's
Mm-hmm.
really hard to see the poles of Io
Yeah.
from
Gotcha.
Earth
Yeah.
because
Yeah.
of geometry, right?
Yeah.
And so we don't have a good understanding of how heat is flowing out of Io near the poles. So that's something that you have to actually go
That would be
to
interesting.
Io or go to the Jovian system in order to measure that. And so basically understanding how heat flows out of Io, we want to just take pictures of the whole surface in infrared and understand how the heat is flowing.
Cool. Very good.
Yeah, and then the last science question that we want to look at is about Io's atmosphere. Excuse me. So you might be surprised to hear that Io actually does have a really tenuous atmosphere. I think it's something like a nanobar.
Yeah.
10 to the minus 9 of what Earth has at the surface.
Mhm.
But there are surface features on Io, and again, we'll have a figure to look at this, that might be dunes, like sand dunes, which are formed by the wind pushing grains around and building them up into dunes.
Okay.
So we know at least a few bodies in the solar system have dunes, and we wanted to see if Io is maybe one of them.
Very cool.
So,
That's new to me. So this will be interesting.
yeah,
Let's roll.
yeah. Io's atmosphere is super interesting. We know that it collapses as soon as Io gets eclipsed by Jupiter because it just gets so cold.
Cool.
But
Yes.
then as soon as it's back in sunlight, there's all this SO2 ice on the surface that gets sublimated and creates that nanobar atmosphere that I was talking about.
Got it.
And that sublimation process might create enough of a pressure gradient between areas with ice and areas without ice that there could be wind. And
Uh-huh.
if there's dust grains, then those dust grains could get picked up by that wind and maybe formed into dunes. So
Very nice.
yeah. So we can keep going and we can look at some of the figures that will
Sure.
explain some of this stuff.
Okay, let's do figure 2.
Yeah, so this figure is about the tidal deformation of the surface, like I was talking about for that magma ocean question.
Mhm.
So the red outline is supposed to show what Io might look like when it's closest to Jupiter, and the blue is when it's far away. And you can see that it both wags around its rotation axis and also the whole moon gets deformed.
Mhm.
And so the surface features, for example, the Planetary, which are like lava lakes, they
Yes.
actually move. And so if you take enough pictures, you can construct something called a geodetic network that
Mhm.
allows you to measure how much these surface features have moved. And then from that, you can calculate these numbers called the love numbers, which will tell you about if there could maybe be a magma ocean or not.
Nice. Okay, very cool.
I love this figure. This is adapted from a figure um
Park.
from Park et al. 2020. They did this for Europa, I think, in
Oh,
preparation for the Clipper mission, which is about to launch next month. So that
yes.
is so exciting. And we would do something really similar for IO.
Very cool. Very cool. Love that figure. Okay. And on figure 3, and here we got some differentiation going on.
Right. Yeah. So this figure shows the different scenarios that could be true for Io's mantle. So if we look at the right part, where where we can see the interior of the moon, the red area on the bottom right has two scenarios that we would call a primitive mantle scenario, which would be either a global subsurface magma ocean or what we call a deep mantle. So you can see that the brown mantle layer is thicker in that scenario than in some of the others.
Oh, yeah. Okay.
So basically, the way that we would look for these different scenarios is by looking at the composition of the lava flows on Io's surface. So lava can be separated into 4 different categories based on how much silica content it has.
Yes.
So if it's got a very small amount of silicate material by weight, then it's ultramafic lava. And if you have a lot of ultramafic lava, that means that the mantle is highly primitive and that differentiation hasn't occurred.
Okay.
Don't ask me details on this. I'm not a geologist, but this is what I've picked up over being involved with this project.
Cool.
And then as you go towards the right on this chart, you get into mafic, intermediate, and felsic materials, which is just having more and more silica content.
Right.
And the more silica you have in the lava, the more differentiated the mantle is. So Earth, for example, would be on the top right in that highly differentiated
Yes.
yellow scenario.
Yes.
And the question is basically, can the tidal heating by Jupiter basically prevent differentiation and keep maintaining this magma ocean, which for Earth, if Earth ever had a magma ocean phase, which I believe it did, that ended, when the planet was really, really young.
Right.
And Io is not really, really young. It's probably about the same age as Earth, but because it has this really different gravitational environment, maybe it has a really different mantle. And the bottom part of this figure where it says the current state of knowledge,
Oh, yeah. Okay.
we have measured, excuse me, the types of lava that we think are seen on Io using telescopes from the ground, for example. We think it's really unlikely that Io is in the same differentiation state as Earth because we haven't seen that felsic material.
Okay.
And ultramafic lavas are also really, really hot compared to other kinds of lava. And there have been observations that are consistent with temperatures that could only be ultramafic lava.
Okay.
It's not really clear if it is ultramafic lava. You can't necessarily tell just from temperature because you could have local, what they call superheating of lava. I guess somehow it gets heated up more after it erupts onto the surface. So a better way of telling if the lava is ultramafic or mafic or intermediate is by measuring the silica content. But we don't have high enough spatial resolution to do that from the ground. So we really have to go and fly past Io and measure the silica content of the lava. And you do that using infrared spectra of the lava.
Yes, exactly. Very cool. Good.
Yeah.
I'm with you. Very nice. All right.
Right.
Okay.
There's a lot of information in that figure.
Between these two, yeah, quite a bit. It's very nice. It's good summary. Good summary. Okay. Here we got some Ionian ridges.
Yeah, so this is on the left, you're looking at the Prometheus region of Io, and you can see those features that look like they might be dunes, like sand dunes.
Mm-hmm.
Um, there's also these sort of ridge features on Pluto, on Mars. We
Oh,
obviously have
yeah.
things on Earth.
Oh,
Uh,
definitely Mars.
and then Comet 67P also has dune features like this. And as a comet, you might expect that it doesn't have an atmosphere, so how
Yeah,
could it have
where's
dune?
that coming from?
Right, exactly. But it turns out comets outgas quite a bit.
Oh
Uh,
yeah.
so uh, gas is released from inside of the comet, and that can actually push grain-sized material on the surface into features that look like dunes. And so, like I said, there's a question of whether Io's atmosphere, even though it's pretty wimpy, there might be strong enough winds to create dune features because
Mm.
uh, they look very similar. And so it turns out that dune, in order to be really called a dune, there has to be very specific um, ratios between things like the length of the dune and the spacing between the crests, I believe. And so there's lots of different tests you can do to see if they are true dunes, if you have like high spatial resolution imagery. So
Mm-hmm.
need to take more pictures, get closer, and see if we can figure out if they really are dunes or if they're sort of cracks in the surface caused by the tidal.
Oh, yeah, 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 yeah.
So yeah, the question is, are they built up or are they caused by the tidal forcing? And so we can
Yeah.
look at things like if they're aligned with the tidal stress
Yes.
direction locally,
Mm.
or if we think they're aligned with how the wind would be blowing and measuring those crust spacing to defect density ratio. I'm not a dunes person either.
Okay.
This is all spelled out in excruciating detail in the paper. So if you're interested in these things, go read the text.
That's why we write these things. That excruciating
Exactly.
detail. It's lovely. Okay, I'm with you. Very good. Okay. We got some dunes. We talked about a little bit about the
Yeah.
atmosphere there.
So that sort of sets up the questions that led to Vulcan's science goals and objectives. So we had two goals. The first one is to characterize the effects of tidal forces on the differentiation state and the crustal features and volcanism of Io.
Okay.
So that covers the first three objectives, which are to determine if there's a magma ocean,
Mm-hmm.
to measure the heat flow out of the Planetary, which we can talk more about what those are, but they're basically like lava lakes.
Mm-hmm.
And then the third goal is to measure the composition of the surface.
Yes.
And then we had or the third objective, sorry. So you have goals and then you have objectives. We had our second goal was to investigate interactions between the volcanoes, the surface features, and the atmosphere. And that maps to our dunes objective.
Mm-hmm.
Yeah.
Mm-hmm. Okay.
Yep. So for objective one, that was just measuring things like the magnetic field, the gravitational field, the love numbers to figure out if there's a magma ocean.
Right.
For objective two, where we are now, we wanted to determine if Planetary are active lava links, which would mean they're like a pool of lava on the surface, but they're directly connected to a reservoir of magma that's being replenished from inside the mantle.
Okay.
Or are they lava ponds? Like if you had a topographic depression on the surface, like you just had a valley and
Yeah.
then a volcano erupted nearby and that lava flowed over and filled the valley. It wouldn't be directly connected to a source of magma, but it would still look like a lava lake. So we call that a lava pond.
Okay.
And you can actually
Yep.
measure the temperature of the lava. And if you are connected to a reservoir underneath, then turns out the highest temperatures will be observed at the edge of the lake, around the whole rim. This has to do with how lava is convected up from inside the mantle, I think.
Yeah.
Whereas if this is a depression being filled in by a lava flow, then you'd expect the highest temperature to be where that lava is flowing in. And so it wouldn't be around the entire rim of the lake.
Interesting. Yeah.
Yeah.
Interesting. Very cool.
So this sort of thing requires taking multiple images of these paterae, both in the visible as well as in infrared wavelengths. And so we would fly over each patera. We identified 10, globally distributed all over the surface of the moon. And you fly over during the day to get dayside images, and then you fly over during the night to get really good infrared images.
Cool.
So you can get the temperature really accurately.
Mm-hmm.
And so each patera is probably different, right? So
Yeah. Mm-hmm.
the idea is to determine if most of them are lava lakes or if they're mostly lava ponds, and each one you have to sort of consider individually.
Yes. Cool. Very good. Good.
Yeah. Oh, and then our third objective is to basically figure out where on that plot we looked at in figure 3 with all the different mantle scenarios, figure out where does Io fall there. So this is the objective to measure the composition and the silica content of all the lavas in different areas. So we identified 10 lava flows distributed all around the surface of the moon that we would go and measure the silica content using infrared spectroscopy.
Hmm.
It's, again, really, we're lucky that Io is so volcanically active, because this is the only body in the solar system that you can just go take pictures of the surface and you know what's on the inside.
Relatively. Yeah.
Yeah.
Very nice.
Cool.
Beautiful, beautiful, beautiful. Okay. Go back to here for 1 sec. Got it. Okay, I'm with you.
Yeah. And so that image that we scrolled by really quickly is the science traceability matrix. So this is one of the most important parts of a mission proposal, where you basically start on the left from the science motivation, and then it's supposed to flow to the right. So you have a science question, and then what measurements do you need to take in order to answer that question?
Yes.
How accurate do your instruments need to be in order to, answer your science goal? And then on the rightmost column, you can set requirements on the mission. Like, for example, I need to measure 10 paterae. I need to measure 10 lava flows.
Day and night.
Right, day and night, and with, some degree of stability. So my image isn't all shaky. Right. And so putting this together is sort of one of the crowning achievements of PSSS. And it's a really important part of any mission proposal. So we don't have to spend any more time on it now. I know it's really small and hard to see, but learning how to put these together was one of my favorite experiences out of the Planetary Science Summer School.
And the detail that is in each one of those, right?
Right.
What is the range? What is your resolution? What is what is the accuracy? Very good.
And so this is actually, if you can believe it, the shortened version.
I'll believe it.
Yeah. So the idea is that anywhere there's a number like towards the right of the traceability matrix, there should be a motivation for that number on the left side. So
right. And these colored boxes in the middle, these are the instruments that would be on the mission?
Exactly. So that tells us which instrument is used to measure each of the observables that go with each physical parameter that we're getting at. So, for example, where you are right now, the mag, that would be a flux gate magnetometer, and it would be used to measure the magnetic field of Io.
Okay, so in this design, looks like you have about 6, 7 different instruments.
Yeah, we have a table in a little bit that shows that we had 2 narrow angle cameras, so really high resolution cameras, a wide angle camera, a thermal infrared spectrometer, 2 flux gate magnetometers. You always have 2 because there are magnetic fields that are, for example, generated by the spacecraft. And you always want to be able to subtract that off so you can see what is the ambient magnetic field and not
Field.
what's being caused by, for example, the currents flowing in the solar panels, right?
Yes, for example.
You always have two flux gates. And then we had an instrument called double IPA because we're grad students and we have to
Double
do something about beer. Um, and this was a
Very
plasma
good.
analyzer, so it would measure ions and electrons and tell you about their energy spectra and the
Yes.
directions that they're coming from.
Cool.
Yeah.
Very good. Okay, well, we'll get down to that table here in a bit. Okay,
Yeah.
covered some of the objectives. And what we got
I
here?
love this figure. So this is a much more digestible way of looking at the science traceability matrix, except
Okay.
for we flipped it around. So now what's on the left here was what was on the right in the science traceability matrix. So this is a figure that illustrates what we call science closure. And so starting from the measurement and the observations that we're going to take, this flows into the physical parameters that we can calculate from these different measurements. And then the fourth column is the different ranges of those numbers that tell us how to distinguish between our two hypotheses in each objective.
Right.
So I'll just pick one and go through it. For example, if we look at objective 3, we would be using our infrared spectrometer and our visible light cameras. We would be imaging 10 targets, which would be different lava flows. And that would take us 9 flybys. And so the targets are the red dots, and then the orbit tracks are the red lines. From those images, we can determine the local silica content using the infrared images. And once we know the silica content of each of those lava flows, because they're globally distributed, then we get an idea of the silica content globally. And from that silica content, we can tell if the lava is ultramafic or mafic to felsic. And then we know if we see ultramafic lava, then we're in a primitive mantle scenario. And if we see mafic to felsic, we know we're in a more differentiated mantle scenario. And then combining this with the measurements we would take for objective 1, we would be able to determine if it's a magma ocean or if it's just one of the other primitive mantle scenarios. And so this kind of illustration is really powerful for example, a review board who you're trying to convince that you've put together a mission that's really going to answer the questions that you're posing, right? So this is one of my favorite figures in the paper.
All right. Well, we might use this one then. Okay. Very nice. Cool. Okay.
I think the next thing will tell us about the instruments. We go to table 2. Yeah, awesome.
Oh yeah, here we go.
Yeah, so this summarizes the most important instrument specs for the instruments that we chose. So obviously in a real mission design, you get to build your instruments, you get to design your instruments from the ground up. That's not really in scope for a summer exercise that you do for 10 weeks.
Yeah.
So what you do for Planetary Science Summer School is you pick analogs from missions that have already flown. So, and then you can make small changes, but you're really using instruments that have already been built and hopefully
Proven.
will answer your science questions in their current state.
Right.
You can make small changes. So for example, we knew that we would have to add radiation shielding to basically every single instrument. But we picked existing instruments that had as close to the specs that we needed as possible. So our narrow angle and wide angle cameras come together as a suite based on the Lunar Reconnaissance Orbiter. And our thermal infrared spectrometer has a lot of heritage. It's similar to what was used on OSIRIS-REx, as well as the Emirates Mars mission. Our fluxgate magnetometers come out of the NASA Goddard group. We would actually use the mini versions, like what would have flown on the GTO set. these are really cool. The entire instrument is less than 600 grams and uses less than a watt of power. And so we have two. So, for basically just over a kilogram, we can get really good measurements of the magnetic field.
Mm-hmm.
And then our last instrument, the dual IO plasma analyzers, has heritage from Parker Solar Probe's SPAN.
Yeah.
And then we would add shielding similar to what was done on Juno Jade. So
Nice, very nice.
yeah, this is a really fun exercise as well because you get to look through, a lot of the literature to find instruments that can do almost what you need them to do, and then you just get to tweak them a little bit. This is much easier on paper than it is in real life. So kind of a relief that we didn't have to really build it and design.
Actually build it right. Because
Yeah.
that's where things come in. Indeed. Okay. Okay, we got our 1, 2, 3, 4, 5, 6 instruments, plus 7 if you count the 2 magnometers.
Yeah.
And what does a flyby look like?
Right. So these are projections of the wide angle and narrow angle camera coverage, and the different colors show the different resolution. On the left panel, that's just from a single flyby. So you
Mhm.
can imagine if we had 78 flybys, as we were really planning to do, we would really cover the whole surface with, pretty high resolution imagery. And then on the right, I think that's from 6 flybys, and that shows where the narrow angle cameras would be looking, and they have much, much higher resolution, but a much smaller field of view. But still imagine multiplying this by 12 or so.
Yeah.
We still get a really good amount of coverage of the surface of Io, basically unprecedented spatial resolution. So that's a really nice
So,
visualization.
yeah, so presumably the mission would be for several years getting many more than 12 flybys, yeah?
Right. So the figure on the right, I think, has 6
Yeah, yeah.
flybys in it, but the total would be something like 78.
Okay,
So the
thank you.
cover, yeah, multiply that by something like 12 or 13. Yeah.
I'm good. Very good. Okay.
Cool.
2, yes. Okay.
I think the next figure shows the spacecraft, and how that would look.
Okay, let me zoom out a little bit. Those are instruments, radio antennas, because we
Yeah.
gotta get
Yeah,
the
so we would
data
use our
back.
radio antenna also for science. It
Yep.
turns out you can you can use the Doppler shift of the radio signal to measure things about the gravitational field of the object that you're flying around. So this is done really often, and this would help us also with our magma ocean question. Um, in figure 8, you can see our spacecraft in the fully deployed configuration. So we would have the magnetometers out on a big boom, and then our gigantic ultraflex solar arrays.
Mhm.
Basically, we're a refrigerator with solar panels. So really fancy high-tech design here.
Flying refrigerators. Very good.
Yes.
Okay, very cool. Got it. Okay.
Great. And then we're now getting into the engineering section, which I'm by
Details.
far not an expert on.
It's
We
all
had,
good. It's all good.
yeah, so I was the principal investigator who is in charge of the science team, and is ultimately the person for a real mission who is responsible for mission success, who's accountable to NASA.
Yes.
But the engineering part is handled by the systems engineer. And so my systems engineer, Quincy McCown, was absolutely fabulous. The mission would have never worked without her. So really, I was really grateful for the opportunity to work with her. And she is the one who handled writing this spacecraft description section.
Well, good shout out. Okay.
Yeah, so I don't know. We can just scroll through here and maybe look at some of the figures. I know there's a couple more figures of the spacecraft. This illustration was actually done by one of our team members, and it shows the thermal subsystem. Really cool just to see the heating moving in and out.
Ooh,
Um, the vault would hold the electronics for most of our instruments to protect them from the radiation in the Jupiter environment. But it's really important to then monitor the temperature of that vault.
yep. Yep.
Yeah,
Very cool. Yeah, we want our refrigerator to work.
absolutely.
Okay. Very good. 9 sets
So
thermal.
each member of the team gets paired up with an employee of JPL to design one of these subsystems.
Oh, nice. Very good.
So you kind of become an expert in your subsystem as well as
Yeah.
contributing to the science and the mission design.
All right. Thermal telecommunications. Ooh, a block diagram.
Yes. Yeah. So this is our telecommunication system. Could not tell you a thing about it, but it would do great science and it would help us get all the data back to Earth. So
There we go. At a rate of about 2 kilobyte per second.
yes, which is not very much.
And a little bit better on the uplink, 7.8. Okay. Oh,
Bits per second,
for
though,
bits.
not
Oh,
kilobytes.
yeah. No,
Yeah.
way
So
lower. Yeah.
the outer solar system is tough in
Yeah.
terms of data rate.
Yes. You have to be patient.
Absolutely.
Patient. Okay. Figure 10. And we get into the mission design.
Yeah. Oh, these are some great figures too. This is the spacecraft in the stowed configuration. So without the solar panels out, so you can see they actually unfold and then unfurl in a big circle. So
Oh, yeah.
that,
Right.
yeah, they're stowed up in like a little wedge, but when they open up, they're round. And so our spacecraft just barely fit inside the 4.6 meter fairing you can see in figure 12, which would be, I think, the Falcon 9.
Oh,
Um,
okay. All
yeah,
right.
just barely fits in there. So we were really happy with that.
Very cool. Okay. Yeah, it is Vulcan. Okay. Very cool. Okay.
Yeah, this is just a breakout of the how much mass is in each subsystem. So you can
Got
see obviously the spacecraft body is the biggest one. The instruments are only 4% of the mass and actually only something like 2% of the overall budget. So
wow.
it's expensive to get into space, even though the science is the driver to go. You end up not getting a whole lot of the budget and the mass budget even for science.
Mm-hmm. Mm-hmm. Interesting. Very good. Okay. Then we got a little bit about the plan maneuvering here and table 4.
Yeah.
How you get
Yeah.
there?
Right. So delta V tells you about how much impulse per unit mass it takes to get somewhere in the solar system.
Uh-huh.
It turns out once you get out of Earth orbit, you can pretty much go anywhere. It takes a lot to get off of Earth, but once you're off, it's much easier to go where you need to go. So our biggest driver for delta V was getting into Jupiter orbit.
Yes.
Um, and we only have a little bit of delta V after that for the science phase. The
300.
best part about this table to me is the 0 for disposal because we would basically just let the orbit decay until we crash in
Crash in.
bio. But we would be able to keep the instruments on as long as possible and get some really great pictures as we get in closer.
Yeah. 5 to 10 years in orbit would be good. So.
We would love that. So this figure shows all the ground tracks of the orbits that we would be imaging on. So the
Okay.
color tells you what the prime target is for that orbit, where the Planetary are in yellow. We have to visit each of those twice, day side and night side. So the dotted and
Yeah.
solid lines tell you if it's a day side or a night side orbit.
Okay.
And then we have the lava flows and then the ridge fields that we would not want to image. So you can see everything's sort of globally dispersed because we really want to make sure we're getting a picture of what's happening globally on the whole moon and not just like one little portion.
Including the pole.
Including the poles, which
Yeah.
I think are not really in this image because it's really hard to image them from the ground. So
Get a little something. We'll get closer anyway.
yes, absolutely.
Very good. Okay.
And then this is similar to the science traceability matrix, but a mission traceability matrix, where you start with the mission requirement, and then that puts requirements on the spacecraft, on the ground system,
Uh,
and how you need to operate everything.
yeah. Okay.
We
Okay.
use the color coding to sort of help you trace because it's not as linear as it is in the science traceability matrix.
10-kilometer accuracy needed. Okay. On your ephemeris. Okay. Cool. Very nice.
Yeah, and then
Oh,
The
yeah.
last sections are risk and cost. Risk is really fun because it's everything in mission design is a trade-off. If something is gonna work really well, it's probably really expensive. If you're gonna get something cheaper, then you need to accommodate a higher risk, and NASA doesn't like risk, right? So everything is you're always doing trade-based studies. And then in terms of cost, we came in at just over $1 billion. That's in FY25 dollars. And that's about what we think the cost cap for the New Frontiers 5 announcement
Oh,
about
yeah, yeah. Uh-huh.
the AO we were responding to. Um, and in table 5, we compared our cost breakdown to Juno.
Yeah.
And we come in really similar. So we were happy with that. Um, yeah, we spent I think a little bit more on um some of these things, but theirs includes the actuals already, and then we have 30% reserves, or 23% reserves kept out. So
Yeah.
all this changes a little bit after launch once you allocate all the
Always.
reserves, but
Always. Yep.
we were happy to see that we were in family with Juno, which
Right.
was the last New Frontiers mission, and also went to the Jovian system. And a fun fact is that Vulcan, the god, is the son of Juno, the goddess, who is the wife of Jupiter. Uh, so it was really fitting to us to send Vulcan as a follow-up to Juno.
Very good. Very good. Regular soap opera there. Yeah. Mhm.
Yeah.
Very cool.
Yeah, so I think for us the biggest lesson learned here was how much can really be done at IO. It's a really exciting object, and it brings together a lot of different parts of the planetary science community that maybe don't always talk to each other. Like I said, I'm a plasma physicist, and this got me really excited about geology and volcanoes. So
Good.
I think that the IO Volcano Observer team should definitely propose again, and that NASA should definitely select them next time, but I'm unbiased, right? So
Got to get it in a decadal survey, and then we'll go.
exactly.
Very cool. Gwen, I want to thank you so much for walking us through your very awesome
Yeah,
article.
absolutely. Thanks for having me.
Sure. Let's see, and you kind of hinted on it a couple of times there, so let me go ahead and push on that a little bit. So what do you think is next, given the published article? Is there going to be a 2024 school? Is
Mhm.
anybody picking this up and potentially running it for a real proposal?
Oh, I wish.
These
But
things that you wish you had considered when you did this originally, these kind of things. So just sort of next steps on mission
absolutely.
planning. Mhm.
Yeah, so there is a 2024 school. They run 2 sessions every single year. So there's a planetary science division. There's now a heliophysics division and also astrophysics. So I highly encourage any PhD candidate or postdoc or recently graduated engineer, if you're interested in mission design, definitely apply. It was a really amazing experience for me. So yeah, I have not shut up about it since I did it in 2022. And I just think everyone can benefit if you have the interest in proposing missions for real one day.
Yeah.
In terms of IO science, the IO Volcano Observer team is still together and still working, and I think they plan on proposing again. So I just really hope that um, folks recognize how cool IO is as an object and how much science there really is to be done there.
Mhm.
And
Mhm.
if a New Frontiers class mission, which is what we designed, is selected instead of a Discovery class mission, which is about half the cost cap, it's really paradigm shifting, transformative science that is enabled by that extra, few $100 million. So I just hope that IO does not get left behind.
Well, I will put you in charge. How about that? Very good. Gwen, thank you so much again for talking about this very lovely project, the summer school and the article. Very nice. Thank you.
Thank you so much for having me.
Yeah, and that will do, everyone. And I hope this made your planetary astronomy day just a little bit better, and we will see you on the next one. Bye-bye.